I'm JM Lastimoso from the GT Velasquez Technological Herbarium. And this is a side project that we've been working on these past few months. And this is a modeling, sort of modeling work wherein we model the current state of our economically important sea species and their projected state in the future. So our study is entitled Habitat Suitability Modeling of Economically Important Sea Species in the Philippines, the current state and future projections. So first let's talk about seaweeds. So seaweeds are a vital part of the ocean, such as they help in stabilizing the sediments, especially in those coralline algae, wherein corals are allowed to settle on those stabilized sediment. Also, they also act as microhabitats for invertebrates and other marine organisms, and most of all, they are an important agricultural product for the Philippines. In fact, the Philippines has over 1,065 known seaweed taxa, making us the most diverse in the tropical Western Pacific. And within those 1,065 taxa, the commercially or economically important seaweed species are grouped into four loosely grouped sections, such as agarophytes, alginophytes, carcinophytes, and the food taxa. They are grouped based on the bioactive compounds that they provide to the industry, such as agarophytes, agar, alginophytes, alginate, carcinophytes, carcinans, and food nutrients for human consumption. So, example of agarophytes are Gracilaria, Deligella, for alginophytes, Sargasso, carcinophytes, the most well-known seaweed, Campophyllus and Eucuma, and food, Caulerpa, or as commonly known in the Philippines, Lato. So, in 2021, BIFAR actually estimated that the seaweed production in the Philippines amounted to around 31.63% of the total fisheries production, which is about 1.34 million metric tons, and the Caribbean value for export is estimated around 205.94 million US dollars. However, with the current changing climate, these projected numbers and our production is in peril. And as we know, there is an increase in sea surface temperature over the years, wherein IPCC actually in 2014 created or projected 4 pathways for the increase in the global temperature, or what they call the representative concentration pathways. However, recent reevaluations have decided that some of the pathways are actually highly unlikely. For example, the RCP 8.5, which was previously known as the business as usual, wherein there will be no change in climate policy, and they projected that in 2100 there will be an increase of 5 degrees Celsius in the temperature. And however, currently, what they accept, the accepted RCP scenario for the world is RCP 4.5, wherein they project around a 2.5 degrees Celsius increase in the temperature. But so, given this increase, and we know that increase in the sea surface temperature has diverse effects on marine organisms, how could we know the fate of our seaweeds in the future? So one way that we could know their fate, or the fate of their areas where we can forage and farm for them, is to have species distribution modeling. So species distribution modeling is done through collecting occurrence points and then relating those occurrence points across different environmental data, usually chosen through a priori, or you choose what you think is affecting them or based on given literature, and then you input them in an algorithm, for example, MaxM, GLM, JM, or GTM, or RF, or some ensemble models, and produce a spatial map which layouts the suitable areas for those species. But one note that should be given is that should be told is that the species distribution model does not tell the probability of a species being present in an area. It only tells the it does not tell that since the area has high suitability for that species, you will find the species in that area. It only says that the area is suitable for the species to live in. So it does not really tell that that species is there. So in this work, we gathered a lot of occurrence points across different public databases and museum databases, mainly from our herbarium, the GT Ecological Herbarium, and from the GBF, or Global Biodiversity Information Facility, and some various foreign herbaria through the microalgae.org portal, as well as through our own fieldworks and published literature. So from those four economically important groups, I chose four representatives in the Castellaria, Sargassum, Topophycus, and Calderpa. And for the environmental layers, I downloaded them from the BioOracle website. So from those occurrence points, I manually checked all those occurrence points and remove the points that have inaccurate coordinates, because sometimes there are coordinates that are planted within land masses, so that's not allowed. So I manually removed them. And then I created a bias file in ENM eval in R to account for the sampling bias. Next, for the environmental data layers, I resampled and restacked them, which means I need to adjust all their spatial resolutions in order for them to have the same resolution, because in MaxSet you cannot run it if they don't have the same spatial resolution. So the spatial resolution of the environmental variables is around 5 arcmin or 9.2 kilometers. Next, I evaluated the correlation among environmental variables using Pearson's correlation coefficient. So I run MaxSet. I first run ENM eval again in R to select for the optimal MaxSet settings, and then I run MaxSet and visualize my figures in QGIS and in R. So for the agarophyte Gracilaria, here is the potential distribution for this red CB. So in present, the main areas that are suitable for Gracilaria, according to the model, is in Sorsogon, in Palawan, and in Sulu Archipelago. And on the right side, you can see the different climate scenario models that was given by MaxSet. So according to MaxSet and its models, for Gracilaria, across different climate scenarios, only the coast of Balabac, Palawan might retain areas that are suitable for the growth of Gracilaria. So next, for the alginophyte Sargassum, as you can see here, same with Gracilaria, Sorsogon, Palawan, Sulu, and Catanduanes, and parts of Dinagat and Siargao Island are highly suitable for the growth of Sargassum. And for the climate models, unfortunately, according to the model given by MaxSet, majority of the coastline in the Philippines in the future will no longer support the growth of Sargassum, which is somewhat unfortunate, I guess. And next, for the Carrageenophyte Capaphycus, this is the potential distribution, and it is also well known that Sulu Archipelago hosts a diverse array of eucalyptoids, plus the farming there is extremely profitable. Also, in addition to Sulu Archipelago, Palawan again and Sorsogon has high stability for the growth of Capaphycus. But fortunately for Capaphycus, according to the model, it will be more resilient across different climate models, such as different habitats across the Philippines actually will remain suitable for the growth of Capaphycus, although it will be less suitable, around 0.5 compared to 1 for the present model. So the areas in Kalayaan Island Group, Palawan, Sulu Archipelago, Quezon and Bicol, Southern Leyte, and Guimaras and Negros will remain suitable for the growth of Capaphycus. And lastly, for the food taxa, Calderpa, as you can see, in the present model, again Palawan, Sulu, Catanduanes, Sorsogon, and Dinagat and Siargao areas are highly suitable for the growth of Calderpa or the top. And in the future climate models given by MaxSet, on the Kalayaan Group, might remain suitable, as well as Sorsogon and in the Guimaras Negros coastline. So in summary, the habitable areas and Garcilaria will contract on both the RCP 4.5 and RCP 8.5 models. And previous habitable areas for Capacaicos might only become less suitable under different climate scenarios. And lastly, and unfortunately, the Philippines might become inhospitable for Sargasso under 4.5 and 8.5 climate scenarios. And what does this imply? So the contraction of suitable sites will lessen the area for sweet farming and foraging for us, resulting in less income and possible depletion of wild stocks. And lastly, the Philippines will also have ecological and trade problems, especially in the loss of Sargasso, since it is our main export for alginate and kelp meal. Now, how do we move forward? So, based on the present spatial models, it is imperative to do more surveys, better marine spatial planning, and targeted management practices on the areas that are highly suitable to the commercially important sea taxa. And number two, force large companies to lessen their emissions. I mean now, because they are the number one reason why we have climate change, I guess. So, number three, and the third is increased support, of course. Increased support on ultra technology development and research on developing resistant strains of seaweeds, specifically Gracilaria, Sargasso, Capaicos, and Cholera. But I still have recommendations for this work. Specifically, I only tested MaxSet in my modeling, and there is still a need to compare it in different modeling approaches such as GLM, JAM, random forest, and some ensemble models. At the same time, I was unable to quantify the level of gain and loss in the habitats across the Philippines, so that is also one area that I recommend to look into. Plus, also review the effects of most environmental variables on the projected suitability maps. And lastly, don't be discouraged since these maps are not accurate. No model is accurate actually, since these do not integrate biotic interactions with adaptations and human interventions. So that is all. Thank you.